The year was 1926, and at Max Born's laboratory in Göttingen, I watched the foundations of 3 centuries of physics collapse in a single semester. Newton's clockwork universe, the same mathematics that predicted Halley's comet to the hour and told artillery officers exactly where their shells would land, simply stopped working when we looked closely enough. What we found instead disturbed Einstein so deeply that he spent 30 years trying to prove us wrong, and he failed. Nearly a century later, physicists still argue about what our discovery actually means, and that's what I want to show you now. You picture an atom as a tiny solar system with electrons whirling in neat orbits around a dense nucleus, like planets around the sun. That was Rutherford's model, and it felt satisfying because it felt complete. But I must tell you something that may disturb your sense of certainty, and it is simply this. That picture is wrong. Not merely incomplete, but wrong. When you understand why it is wrong, you will begin to see why the greatest revolution in human thought did not end with answers, but ended with questions we still cannot resolve. When I arrived in Germany as a young man of 22, I was already convinced I understood the physical world after studying at Harvard and working at the Cavendish Laboratory in Cambridge. Within months, Göttingen disabused me of that certainty because the old world was dying, and we were its pallbearers. We had inherited a universe that seemed knowable in principle, if not always in practice, because Newton had given us a clockwork cosmos. The same equations that launched ships across oceans and predicted eclipses centuries in advance made physics not merely successful, but arrogantly successful. Laplace had boasted that given the position and momentum of every particle in existence, he could calculate the entire future of the universe, and the past too, since time runs backward as easily as forward in those equations. There was something deeply consoling about this vision of a universe governed by iron laws, where uncertainty was merely ignorance, and ignorance could always be overcome. This was the world we were taught to believe in, and then it collapsed. The first cracks appeared not in some exotic realm, but in the most ordinary of phenomena, which was light itself. A heated piece of metal glowing red, then orange, then white, produced a spectrum that defied everything classical physics predicted. What Max Planck found in 1900 was that he could explain it only by assuming that energy comes in discrete packets called quanta, rather than flowing continuously. Nature at its foundation turned out to be digital, not analog, not continuous, but grainy. This was decades before computers, and Planck had discovered that the universe runs on whole numbers. He thought it was a mathematical trick, a provisional device, but it was not a trick at all. It was the first glimpse into a world where the continuous gives way to the discontinuous and where nature operates not by smooth gradients but by sudden jumps. And then Einstein, that magnificent and stubborn man, showed that light itself behaves as particles called photons, even though we had spent 2 centuries proving it was a wave. The photoelectric effect made no sense otherwise, which meant that light is a wave and light is also a particle. Hold both thoughts in your mind at once and you begin to feel the vertigo that seized us all. But it was Niels Bohr who truly shattered the old world with his 1913 model of the atom, where electrons were confined to specific orbits and leaped instantaneously from one to another without traversing the space between. An electron does not spiral gracefully down into the nucleus while radiating energy continuously, but instead jumps, existing here and then there, with no trajectory connecting those 2 states. Bohr knew this was radical, and he also knew it was true. Think about what that means in the classical world, where getting from one place to another requires passing through all the points in between, which is what motion is. In the quantum world, an electron can be in one state and then another with nothing in between, and this is not a failure of our instruments to detect the intermediate states, because there are no intermediate states. The electron does not take a path we cannot see, but takes no path at all. This should trouble you because it troubled us. By the mid-1920s, the situation had become intolerable, since we had pieces of a theory, including Planck's quanta, Einstein's photons, Bohr's atomic model, and Louis de Broglie's matter waves, but no coherent framework. The old language failed us completely. Position, velocity, acceleration, and force, which were the very terms in which Newton's equations were written, turned out to be not simultaneously applicable to the atomic world. We had almost lost the concept of equations of motion, having discovered that the foundations on which they stood did not hold at this scale, and that's when a new mechanics emerged in the span of a few feverish years. Werner Heisenberg, working in Göttingen under Born, constructed a purely mathematical scheme using matrices of observable quantities that made no attempt to visualize what was happening inside the atom. He simply asked what the relationships were between things we can actually measure, and the answer was a new kind of algebra where the order of operations mattered in ways classical mathematics never anticipated. Multiply position by momentum, and you get one answer, but multiply momentum by position, and you get a different answer because the commutator of these quantities is not zero, but Planck's constant. Like notes in a melody where C followed by G is not the same as G followed by C, the quantum world has a grammar, and that grammar is non-commutative. This was no accident, but the beating heart of the new physics. Wolfgang Pauli, with whom I had studied in Zurich, was the sharpest critic among us, and once dismissed a theory as not even wrong. Even he was forced to accept what Heisenberg had found, because the uncertainty was not in our knowledge, but in nature itself. Erwin Schrödinger, meanwhile, approached the same problem from an entirely different direction, by writing down a wave equation that was elegant and familiar in form and seemingly classical, describing how a quantum system evolves in time. His waves were not waves of matter or energy in the usual sense, but waves of probability, where the square of the wave function at any point gives you the likelihood of finding the particle there, not the certainty, but the likelihood. Born gave us the rule for extracting these probabilities, what we now call the Born rule, and it has never failed. Two approaches that were utterly different in appearance both turned out to be correct, and both described the same reality. Paul Dirac soon showed they were mathematically equivalent, two languages for the same truth, and this complementarity, this coexistence of seemingly incompatible descriptions, would become the signature feature of quantum mechanics. At the Solvay conference in Brussels in 1927, Einstein and Bohr debated these questions for days while I was not there, but the arguments reached us like dispatches from a war. Einstein could not accept that God played dice with the universe, and Bohr replied that we should not tell God what to do. The intellectual combat was fierce and continued for decades, and even though Einstein was the greatest physicist of his generation, on this question he was wrong. Here is where most people stop because they learn the formalism, master the mathematics, calculate cross-sections and energy levels, and think they have understood. They have not. Understanding quantum mechanics is not a matter of learning to compute, but a matter of grasping what the theory says about the nature of reality, and this is where the haunting begins. Let me put it plainly. Quantum mechanics is not causal. There is no complete causal determination of the future on the basis of available knowledge of the present, because the law of quantum mechanics restricts, but does not, in general, define the outcome of an experiment. It tells you what can happen, and with what probability, but it does not tell you what will happen. Think about what that means in the Newtonian universe, where complete knowledge of the present state of a system allows exact prediction of its future in principle. The future is contained in the present like the oak is contained in the acorn, but in the quantum world, the present does not contain the future in this way. Given identical initial conditions, truly identical and not merely apparently so, two experiments can yield different results. And this is not because we are ignorant of some hidden variable, but because there is nothing more to know. The Newtonian universe of cause and effect did not merely become more complicated at the atomic scale, but vanished entirely. And here's the thing, it gets stranger. Consider measurement in classical physics, where it is passive and the moon is where it is, whether or not you look at it, with your active observation revealing a pre-existing fact. In quantum mechanics, measurement is active and does something, because every observation on a system reveals new knowledge as to what its state is that did not exist before and could not have been obtained by analysis and mathematical computation. Every intervention to make a measurement creates, despite all the universal order of the world, a new and unique situation that is not fully predictable. The measurement did not reveal a pre-existing fact, but brought a fact into being. And think about what kind of universe that implies. Not a universe of objects waiting to be discovered like continents on an uncharted map, but a universe that responds to inquiry, a universe that in some sense is listening. This is often misunderstood because people imagine that quantum mechanics makes reality somehow subjective, that consciousness plays a special role, and that the observer must be a human mind peering at dials. That is wrong. The division that matters is not between the mind and the world, but between the object of study and the means, the apparatus used to study it. The quantum world has not lost its objective quality, but attains this objectivity through those interlockings with experiments we use to define one or another of its properties and to measure it. The apparatus is not a neutral window onto a pre-existing reality, but is part of the phenomenon itself. Change the apparatus, and you change what you can say about the system. Not merely what you can learn about it, but what you can say about it. Position and momentum require different experimental arrangements to measure, and these arrangements are mutually exclusive. You cannot build a device that simultaneously measures both with arbitrary precision, because this is not a practical limitation, but a feature of reality. To set up an experiment to measure position is to make momentum undefined, and vice versa. Bohr called this the principle of complementarity, and it was his deepest insight, the one most often trivialized or ignored. What came to be called the Copenhagen interpretation, though we never use that phrase ourselves, rests on this foundation. Complementarity is not merely the statement that some properties cannot be measured simultaneously, but the recognition that certain concepts like wave and particle, position and momentum, determinism and discontinuity can only be applied in mutually exclusive experimental contexts. Both are necessary for a complete description. Neither is complete on its own, and they cannot be combined into a single unified picture. This is not because our language is inadequate, though it is, but because reality at this level does not conform to our expectation that there should be a single consistent story we can tell about what is happening when we are not looking. There is no such story. Or rather, the question itself has no meaning. To ask what the electron is doing when we are not measuring it is to ask a question that the theory cannot answer, not because of some limitation, but because the question presupposes a classical picture that does not apply. Let me make this concrete with the famous double-slit experiment. A beam of electrons is directed at a barrier with two narrow slits, and on the far side a screen records where each electron lands. If you simply let the electrons go through and record where they arrive, you see an interference pattern with bands of high and low intensity, exactly as you would expect for waves passing through two slits and interfering with each other. But electrons are particles that arrive at the screen one at a time, leaving discrete spots, so each individual electron goes through one slit or the other. Watch and see what happens. If you place a detector at the slits to determine which one each electron passes through, the interference pattern vanishes. Now you see two simple bands, one behind each slit, exactly as you would expect for particles, because the mere act of determining which path the electron took destroys the interference. This experiment has been repeated with electrons, neutrons, atoms, and even molecules as large as Buckminster fullerene, which is 60 carbon atoms moving as one, and the result is always the same. When you do not look, the particle behaves as if it passes through both slits simultaneously, interfering with itself. But when you do look, it behaves as if it passes through only one slit. The electron is not secretly going through one slit or the other with our ignorance creating the appearance of interference, because the interference is real when we do not measure which slit. The definite path is real when we do measure. The electron does not have a path when we are not measuring path, and does not have a definite position at the slits when we are measuring something else. This is what I mean when I say that measurement creates something new, because before the measurement there was no fact of the matter about which slit the electron went through. After the measurement there is, and the measurement did not reveal a pre-existing fact, but brought a fact into being. A lawyer once asked me if quantum mechanics meant that witnesses were unreliable, that observing a crime changed what happened, and I told him it was worse than that. In quantum mechanics, before you observe, there may be no fact of the matter about what happened, and the crime and the alibi exist in superposition until someone checks. He did not invite me back. Now there is a temptation, an almost irresistible temptation, to rebel against this picture. Surely there must be some deeper level of description, some hidden reality beneath the quantum formalism, where things have definite properties whether we measure them or not. Einstein felt this temptation more powerfully than anyone because he could not accept that God played dice with the universe. He spent decades searching for a way to restore the classical picture, to find variables hidden beneath quantum mechanics that would make the randomness merely apparent. In 1935, with Boris Podolsky and Nathan Rosen, he published what he thought was a devastating critique called the EPR paradox, arguing that quantum mechanics must be incomplete. He was wrong. And not merely unproven wrong, but demonstrated wrong because the experiments have been done. In 1964, John Bell showed that any local hidden variable theory must satisfy certain inequalities. And in 1982, Alain Aspect and his team in Paris performed the definitive test. The quantum correlations violated Bell's inequalities exactly as quantum mechanics predicted, which meant the hidden variables Einstein sought do not exist. The indeterminacy is not a veil over deeper certainty, but the bedrock itself. The experiments have been repeated with increasing precision by Anton Zeilinger in Vienna, by teams in Geneva and Boulder and Shanghai, and every time quantum mechanics is vindicated. The world does not have definite properties waiting to be discovered because some properties come into existence only when measured, and which properties those are depends on how you choose to measure. This is not mysticism but physics, and it is the most precise, most tested, most successful theory in the history of science. Every time someone has tried to prove it incomplete, the theory has been vindicated. Every new domain we explore, from superconductors to lasers to the quantum computers now being built in laboratories around the world, confirms its predictions with breathtaking accuracy. The quantum world is strange but not optional because it is the world we actually live in. And yet the theory itself remains incomplete in a way that troubles anyone who thinks carefully about it, which is what we call the measurement problem. The formalism gives us two different kinds of evolution. Between measurements, the wave function evolves smoothly and deterministically, according to Schrödinger's equation, but upon measurement, the wave function collapses instantaneously, discontinuously, and probabilistically. These two kinds of evolution are mathematically incompatible because the smooth evolution preserves all possibilities and maintains all superpositions, while the collapse selects one possibility and destroys the rest. John von Neumann formalized this beautifully, and the problem only became starker. What counts as a measurement and when does collapse occur are questions the formalism does not answer. Bohr insisted that we must describe the apparatus in classical terms, and that the line between quantum system and classical observer is necessary for making predictions but movable in practice. And this works for calculating outcomes, but does not tell us what is really happening. Some say the collapse is real, that at some point quantum superpositions genuinely end, and definite outcomes genuinely occur, but they cannot say where, or when, or what physical process is involved. Others, following Hugh Everett, say there is no collapse, and that all possibilities continue to exist, branching into parallel worlds we can never observe. My former student David Bohm proposed that particles do have definite positions at all times, guided by a pilot wave that produces quantum statistics. Still, others say the wave function is not a physical thing at all, but merely a tool for calculating probabilities. And the question of what really happens is meaningless. I have my own views on these matters, but what strikes me most forcefully is how open the question remains. Nearly a century after the basic formalism was established, we still do not agree on what it means, and the most successful physical theory ever devised still leaves us unsure of its ontology. We know how to calculate, but do not know what we are calculating about. Richard Feynman, who worked with us briefly at Los Alamos and went on to reformulate quantum mechanics in his own way, once said that nobody understands quantum mechanics. With respect to my former colleague, I disagree. We understand it quite well, but what we lack is not understanding but acceptance. We understand the mathematics, but do not accept what it implies about reality. This is what haunts physics, not the strangeness of quantum mechanics because we have grown used to that. What haunts us is that the strangeness runs deeper than calculation, and deeper than prediction, into the very question of what physical theory is supposed to tell us. Is physics about describing an independent reality or about systematizing our observations? And is there a world out there with definite properties or only phenomena that emerge through our interactions with nature? And does the wave function represent something real, or is it merely an instrument for bookkeeping? These are not questions physicists can ignore by retreating into pragmatism because they matter for the future of physics. The search for a theory of quantum gravity, for a unified description of all forces, runs into these foundational issues at every turn. The structure of space-time, the nature of black holes, and the origin of the universe all connect back to questions about what quantum mechanics actually says about reality. If we do not understand the theory we have, we cannot hope to extend it. At Berkeley, I taught my students Sanskrit so they could read the Bhagavad Gita in the original, and they thought I was eccentric, but I thought I was preparing them to understand physics. The general notions about human understanding, which are illustrated by discoveries in atomic physics, are not wholly unfamiliar or wholly unheard of. Even in our own culture, they have a history, and in Buddhist and Hindu thought they occupy a more considerable and central place. What we found in quantum mechanics is an exemplification, an encouragement, and refinement of old wisdom, that the observer cannot be separated from what is observed, that knowledge and the known arise together, and that the attempt to describe nature in terms of isolated objects with definite properties misses something essential about how reality is constituted. I do not say this to mystify quantum mechanics or to claim that ancient sages anticipated modern physics because the parallel is not exact, but it is suggestive. And it suggests that the difficulties we face in interpreting quantum theory may not be technical problems awaiting a clever solution, but may reflect something deep about the relationship between mind and nature, between knower and known, that Western science has been slow to acknowledge. The measurement problem may not be a problem to be solved, but a feature to be accepted, like asking why mathematics works at all. The demand for a single consistent story about reality, independent of how we inquire into it, may be the prejudice we must abandon. Let me leave you with this from my Wreath Lectures for the BBC in 1953, where I tried to explain these matters to a general audience. Science starts with a preconception, with common sense, and it moves on to observation, is marked by the discovery of paradox, and is then concerned with the correction of preconception, moving then to further observation and more refined experiment. What we have learned about the atom is of this kind, a correction of our common sense preconception so radical that it forces us to reconsider what preconception itself means. The atom is not a miniature solar system, and the electron is not a tiny planet, and matter is not made of little billiard balls. Reality, at its most fundamental level, is not a collection of separate objects with definite properties existing independently of how we inquire into them. Reality is relational and contextual and participatory, and what we find depends on how we look. There is no view from nowhere, and no description of the world that does not include the means by which the description is obtained. This is not a limitation to be overcome, but the truth to be understood. The physicists have known this for decades and use it every day in every calculation, and yet they continue to debate what it means, because the implications are so profound that we have not yet found the language to express them, the concepts to contain them, or the philosophical framework to make them our own. That is what quantum mechanics understood about nature that still haunts us. Not the uncertainty and not the probability and not even the non-locality or the entanglement. What haunts us is the recognition that the world does not come to us pre-packaged into objects and properties, that the divisions we make between observer and observed, and between subject and object, and between knower and known, are not given by nature but imposed by our experimental choices, and that a complete description of reality must somehow include the perspective from which the description is made. We are not outside the universe looking in, but part of the world we seek to understand, and understanding that, truly understanding it, changes everything. That is what we discovered and what still haunts us. And that is why quantum mechanics, for all its success and precision and technological marvels, remains the unfinished revolution in human thought. We have learned how to calculate, but have not yet learned how to comprehend.